So welcome to my to the main part of my core data talk. And you know, it's funny, this whole setup here that I'm flying in from Berlin and I'm standing here on the stage in front of this great community in Stockholm to give a talk and giving an interview here before with Alec, and all this is kind of antithetical to my message that I want to transmit to you today. And to start, I want to bring up a small analogy. Imagine a son comes to his father, and he says something like, "Dad, can I ask you for some advice? I have this great group of friends, and we share a lot of common interests, and it's really every time I'm together with them, we are doing all this cool stuff, and we are having a great time. But then sometimes I have the feeling that I have to be this fun guy to be with them. And I'm not sure if I can always really be myself with them. But then I have this other small circle of friends. And I really like them because we can have these great deep conversations about all these meaningful things in our lives. But then sometimes I really notice actually we don't have so many interests in common. And I feel this obligation to find things for us to do together. And what do you think? With whom should I spend more time? With this one group of friends or with the other group of friends? And in this analogy, I don't want to be the parent who tells his son, like, well, son, it's clear these people are not good for you. You should go to these people and you should hang out with them. They will bring you on a much better path. I would want to be the father who talks to his son about the values that are important to me to have meaningful, long-term, deep friendships. And so that my son is able to and is equipped to decide for himself what he wants in a friendship and what is more important to him, so that he can make the decision and not want my advice on the result. And so with this, to stick with this analogy, me being here today on stage and talking about core data, I don't want to be the guy to tell you what's the right way to use core data. I don't want to be the guy who tells you, you have to set your stack up like this. Because I can't tell you that. Because I don't know your specifics. I don't know your constraints. I don't know your preferences even. But what I want to do is I want to encourage you and I want to show you how you can reason about these things for yourself without referring to anybody you might assign authority to in this field, be it me, be it some guy on Stack Overflow, be it Markus Zara, be it whomever. I really want to encourage you to think this through for yourself and to make the best choice for yourself instead of looking for somebody who tells you you have to do it like that. And so this is at least my intention tonight, that I will try to to resist the urge of telling you you have to do it that way, but I will try to explain you things and also show you how you can find out these things yourself, how core data works, so that you can make the best decision in the end. So the title of my talk is actually in my slides, it's Pragmatic core data, and before it was non-dogmatic core data. So I mixed this up in my head, but non-dogmatic probably wouldn't fit either way on the slide. So, but that's what I mean with pragmatic or non-dogmatic at this point. I mean, there is not the canonical way of use core data the right way. Core data is a super flexible framework, and you can do a lot of different things with it, different setups, different approaches, and they have different trade-offs. So I would like, before I start to get into some more technical stuff, I would like to get an overview. Who of you has worked with core data before? Okay, thanks. That's quite a lot of hands. So for those of you who haven't worked with core data, I still hope that you will get something out of this talk. And even if it's just like, maybe you remember some snippets and one day when you might have to use it, maybe you will remember. And even if you just remember my advice to not just take things for granted that somebody with a name says. So as we mentioned before, we talked about before, I'm in the process of finishing up this book. I'm writing this together with Daniel. And so this process of figuring stuff out and finding out how core data works and how it behaves and what it does under the hood is very fresh in my mind still. And I want to try to communicate some of that to you. With core data, I think there are two big topics that come up again and again. And that's performance and concurrency. Performance, because, well, it's a persistency framework, and we are dealing with disk I/O, which is inherently slow, really slow, like compared to everything you do in memory. So you run into performance issues sometimes here and there, and since you do, you use concurrency to solve them, and then the saying goes, you have another problem. And I want to talk a bit about both of those aspects with core data. But as I said, I can't tell you what's the right way to get great performance or to do concurrency. But I want to show you how to reason about this for yourself. And in order to reason about it, it's really important to understand the framework. When you understand the framework, when you really know what happens in response to whatever you do, like executing a fetch request or saving a child context or whatever it is, then it becomes pretty straightforward to reason about if what you're doing is a good idea or if it's a bad idea. So let's jump in about some things related to performance. When we talk about performance, it's super important to look at the architecture of core data. You've seen this before, probably. I just noticed that I'm completely powerless with my laser pointer because the screen's there. So yeah, it doesn't matter. It's a typical picture. You probably have seen this before. You have the managed object context at the top. You have the persistent store coordinator in the middle, and then you have SQLite at the bottom. And I'm just going to assume here that it's always SQLite for now, just for simplicity's sake. And you can think of these three layers of core data as the three performance tiers of core data. So you have the context tier at the top, the coordinator tier, and the SQLite tier. And whenever you have to drop down another tier for some operation, you are going to incur a performance hit. So I will talk about each of these tiers a bit more in detail. The context tier works entirely in memory. And it's not thread safe. And that it's not thread safe is actually a design feature. Because this top layer of core data, the managed object context, with its managed object inside, is designed to be not thread safe so that it can be really, really fast. And that it can have predictable performance characteristics because it's log-free. You cannot get into the situation that you make some call on a context and you run into contention. Somebody else is working with this context. Since it's not thread safe, this cannot happen. You are, of course, the flip side of this is you are responsible to use it only from one queue. But so that's what makes this the top tier the fastest one. It's in memory. It's not thread safe. So what can you do within the context tier? So for example, you can call APIs to test whether an object is a so-called fault or not, if the object has already been populated with data or not. You can test that. This will not drop down into the lower layers. You can access properties on objects that are populated with data entirely in memory operation. You can traverse to one relationships, or you can traverse to many relationships if you have accessed those before. Second time, everything is only in the context tier and in memory only. So you can also fault in objects with a specific ID. So when you call object with ID on the context, you are going to get back an object, mostly a fault. And also this happens entirely in the context tier and therefore is very, very fast. You can get objects that are registered in the context already or check if they are registered in the context with this API. You can make any kind of change. You can set properties on your objects. You can change relationships. All this happens entirely in the context. And you can, when you save a child context, this is also in memory only. However, That's why I put the brackets around. You still can run into contention issues if your parent context runs on a different queue, something like that. There could be contention. It's kind of a gray area. It's an in-between thing. So let's look at the coordinator tier. The coordinator tier is also entirely in memory. But the coordinator tier is thread safe. And therefore, you can run into potential lock contention there. So the coordinator is now this building block where you can connect multiple contexts to. So therefore, it has to be thread safe. If you use, or let's say more generally, if you don't run into contention, accessing the coordinator tier is very fast. It's still only in memory. The performance hit you incur is not very big. But it gets harder to reason about it, because if you have some background activity maybe working on with the same coordinator, you don't know upfront. You can't know a priori if how fast a certain call will be, because you might run into a contended coordinator. So when do you drop down into the coordinator tier and only into the coordinator tier? There's basically just one case. Maybe, I don't know if I missed something, but so if you access a property on an object, which is a fault, but whose data is already in the coordinator's row cache. So the coordinator, in the coordinator tier, or to be more precise, in the persistent store, there is this row cache where Core caches all the raw data it loads from SQLite for all the objects you're working with. So if you have an object which is not populated with data, and then you access one of its properties, then Core can go into the coordinator layer, and it can retrieve this data from the row cache. And this is a pretty fast operation because it's in memory only. And maybe as a side note, it's good to know this behavior of the row cache, which is pretty opaque. It's not documented very well, but it's very it's completely predictable. So this is not a cache which will just start to discard stuff when there are more than 1,000 objects in it or something like that. This thing behaves completely deterministically, and you know that when you have loaded data from SQLite, the data goes into the row cache, and it will stay there as long as a managed object is alive which references it. Yeah, so the stuff is reference counted. If the last managed object goes away, which refers to a cache entry, the cache entry will go away. So then we come to the lowest level, to the SQLite tier. There we have to do disk I/O, so it's inherently slow, and it's inherently difficult to reason about it. Because you might have a small database, and after the first time you access it, maybe most of it is in SQLite's page cache, and every next access will be very fast, but you don't know really. You might have a big database, and you will have to go back to disk a lot. If you have to go back to disk, you don't know what else is going on in the system. So how fast will your disk access be? You don't really know upfront. So this becomes more unpredictable, but generally you have to assume every time you go down there, it will be slow. Just because disk I/O is just insanely slow compared to what you can do in memory. And it's thread safe, because as SQLite you can use SQLite concurrently from multiple threads. So you can also have potential contention there, although SQLite is pretty good at handling that, but we will come back to that a bit later. So when do you have to drop down to the SQLite tier? The main thing is when you execute fetch requests. And fetch requests by API contract go down to the SQLite store, or to whatever store you have. So this always executes this complete round trip down to the store, fetches the data, and comes back. And there are a bunch of configuration properties on the fetch requests which determine what exactly is going to happen there. And I'm not going into all of them. You can read this stuff up in the documentation, the API documentation, and some other places. But let's take a quick look at this process of executing a fetch request. So this looks something like that. Yeah, it's a bit small maybe for the last rows, but so anyway, you call execute fetch request on the context. This will forward your request to the coordinator, which will forward the request to the persistent store. And the persistent store will translate your request into an SQL query. It will send this query to SQLite. SQLite will execute the query, and it will give back the raw data to your persistent store. Your persistent store takes this raw data, stores it in the row cache. Then the persistent store uses the reference it has to the context and instantiates all these managed objects you have asked for, and then it gives back these object faults to the context. The context then starts checking if it has any pending, any unsafe changes which also fit your query, accounts for them, and then gives you back the result. And so this is for a standard fetch request. No special configuration option set. And now you can start modifying this behavior with all these different flags. So for example, you can say, what was it? Includes property values. You can set this flag to false on the fetch request, which will cause core data to execute a query in SQLite, which doesn't include the actual data. It will only load the object ID and some other things. But it will not load the actual data. So sometimes this can be useful. For example, something like if you use fetch batch size on a fetch request. This internally uses something like that. So there are use cases for that. You can, for example, switch off includes pending changes. So the context will stop doing this check at the end if there are any unsafe changes it has to include. And also there, a little side note, this includes pending changes thing, where the context tries to figure out if it has any changes that match your request. This is like working halfway. Yeah? So this is because normally your predicates get translated into SQLite as queries, and the context has to re-implement all of that to check in memory, and it's not complete. So I just checked briefly before. I tried this for a predicate that traverses a relationship. So like any relationship dot something, this didn't work. So this is something just to watch out for. But these things, I really want to encourage you at this point with these kind of options when you want to try it, when you want to find out what they are really doing, if they are doing what you think they do or they should do. It's super helpful to just set up small test projects. Just create one entity or two entities, put a few objects in, it's just a couple of lines of code, and enable the debug flags and use a lot of print statements and figure this out. I have like dozens of them somewhere for the process of figuring this stuff out. Okay, so when do you have to drop down to the SQLite tier other than executing fetch requests? Well, saving, of course. When you save a context that is connected to a coordinator, you have to go to the store. This is a Synchronous API, so you are going down there to SQLite to save the data to disk. And that is an important one, when you access a property of an object, which is a fault, so it's not populated with its data yet, and the data is not in the row cache. Core data has to go all the way down to the store and come up back to the context with the data, just for this one property. So this, if you do this a lot, if this happens a lot in your app, then you can run into problems there, into performance issues. But as I said, the nice thing is you don't have to take my word for any of that. You can use a bunch of tools to just try this out, to figure this out yourself, to test your specific use case, like the core data instruments. There are 4 of them. You have to watch out for in the default template, in the core data template in instruments, there are only 3 of them included. There's one more, so check the instruments library. There's one more very useful instrument. I think it's the false instrument or something like that. So you get 4 instruments, one fetch request instrument, one save request instrument, one fault instrument, and one cache misses instrument. So you get a lot of information there. You can really see when are you accessing a fault and core data has to drop down to a lower level to access data. Then you can check the cache misses track and see when you had to drop down because the object was a fault. Did you also incur a cache miss? You had to go down to SQLite. All these kind of things you can see here in a very nice way to see if you might have performance issues there at some level. And of course, you can enable this launch argument, this SQL debug launch argument, which will put out stuff like that onto the console. Basically, it spits out these SQL queries. Super handy to figure out what core data is doing, actually. So if you look at the second last line, it says fault fulfilled from database for some object. That tells you that you have access to property on an object, which wasn't materialized, and the data wasn't in the row cache. So core data had to go down and execute the query you see at the top to fetch the data. If you see lots of those, you might or might not be in trouble, depending on how often this happens. So the ultimate question, like, how do I get best performance with core data, is the question that I can answer in the abstract. So I think your best bet is to look at this architecture, to understand this architecture, and to see how do these different layers work, how are the performance characteristics of these layers, and then reason about your app's behavior with this background knowledge. And when you do that, you can make the right choice for your specific project. Because if I try to make these recommendations in the abstract and tell you should use as little fetch requests as possible, well, first of all, what does that even mean, right? What's as little as possible? Theoretically, I maybe can get away with one for one root object, and then I only traverse relationships. That I might get terrible performance with that. So this general advice is super difficult to give. You really have to see what's your specific problem, what's your use case, what are your constraints, and reason with this specific information based on your understanding of what happens down in this core data stack. I have water somewhere. That sounds funny on the speakers, probably. Okay, the other very hot topic is concurrency. So this is not as nice as the fireside thing before, but at least. So in concurrency, there is this big question floating around on the interwebs, like to nest or not to nest, right? It's this different setups you can make with core data. Should you use nested contexts, or should you go down the more traditional route using these parallel contexts? And in the book we are writing, we recommend pretty strongly to at least consider and really think this through very carefully if the nested setup is the right one for you. That doesn't mean that you shouldn't use that ever. And we list use cases for nested contexts. But it's a really good example of the problem when giving these general recommendations. Because when you write in the abstract and we write this for a broad audience and we don't know who this audience will be and what kind of problems you're facing, what kinds of use cases you have to account for, it's really hard to say anything specific, to say you should do it like that. Because every time you get too specific, you will probably be wrong for some part of people. But you want to say something, right? So you're going this, it's this balance between not saying too specific things, not saying too strong things in terms of you have to do it like that, but you still want to give some good guidelines and some good recommendations. So it's a fine line to walk. And yeah, so don't take our word for it. If we say we recommend you do this or that, don't just believe it and do what we recommend, but check if this holds up, if you think this through in the context of your specific circumstances. So let's just stack up the evidence for different kind of concurrent core data setups. Let's start out with this traditional setup, parallel contexts. Yeah, so it's a simple stack. You have one coordinator, and then you have these two contexts on top. A main queue context where you do all UI work, and a private queue context where you do whatever background work you have to do, usually some importing from web service data or something like that. So the advantages of such a setup are that when you execute requests in one of these contexts, they don't block the other context's queue. So the only time you, if you execute two requests basically at the same time in both contexts, you will run into contention at the common coordinator. But if you just execute a lot of requests, for example, on your background context, your main queue will be free. It will be not blocked. And merging changes to reconcile the things you have changed in both contexts. When you do this with merging these save notifications, right, from one context into the other. And this merging process can ignore all the changes that are not of interest to the other context. So if you make updates to objects that are not even registered in the other context, core data can just skip them and doesn't need to consider those changes. So this is a performance win when reconciling changes. Disadvantages of the setup are, for example, that saves on the UI context cause disk I/O on the main queue, right? If you have to save a lot of data, some data in the UI. Let's say you have copied a huge document into something, and then you hit save. Then save is a synchronous API, so you are doing I/O on the main thread. If this is a problem, I don't know. Only you can know for your use case. For a lot of things, small things, iOS apps, you create a couple of records, this is not an issue. It might be an issue for a complicated app. You have to check that. Another contender in this area is a setup with multiple coordinators. That's something I think Apple also has talked about a couple of times over the last years, that you have the possibility to set up two complete separate stacks which share an SQLite database at the bottom. So you have two persistent store coordinators and one context on top of them. So the advantages of such a setup are that now the context and the coordinator tier are separated. So they are completely independent of each other. You can work in both contexts at the same time without running into contention at the coordinator level. Now you have pushed down the point of contention to SQLite. And SQLite is better at handling concurrency because it can handle multiple reads and a single write at the same time. And the coordinator, of course, since this is simply, if one context uses the coordinator, it takes a lock and that's it. Doesn't matter what it does, if it reads or writes. So this can be a performance win for heavy background work. The disadvantages, however, are that those stacks don't share the row cache anymore. So if you do a lot of background work in the background stack, and then you save, you take this save notification, you merge it into your main stack, none of the data you have worked with or imported or whatever is in this main stack's row cache. So any object, when you access one of these objects, it has to go to disk all the time to get this data because the row cache is not shared. So this is something to watch out for. You can work around that. You can take measures to mitigate this issue. Maybe you have to refetch some things globally when you merge and change save notifications, something like that. But it's a disadvantage to be aware of. And it's a minor disadvantage. You can't share object IDs directly between these two stacks because object IDs are bound to a persistent store. So you have to use their URI representation and jump through some hoops to get back to the object ID. So now finally, let's get to our friend, the nested contexts. So this is a setup. It would look something like that. Yeah, you can stack these things together in all kinds of different ways. I'm just taking one example. So you would have now these different contexts stacked on top of each other. And this is this nested context API Apple introduced with iOS 5. In this case, we use the persistent store coordinator. We put a private context on top, then the UI context, and then another private context or multiple of them to do our background work. So our background work would be done in these worker contexts at the top. So the advantages of the setup are that if you save stuff from the main context, for example, the scenario I mentioned before, you copy in tons of data into your app, just copy paste and you save. Now the save doesn't block the main thread anymore, because the save of your UI context only pushes all the stuff down into this private context that's below. And the private context can save this later asynchronously. So it's one of the major advantages and one of the major reasons nested contexts were introduced with iOS 5, where this iCloud syncing stuff came in. And another advantage, kind of an esoteric advantage, is that maybe the people who have worked with core data have run into that. You can have this issue when you work with multiple contexts and you delete an object. There is this time slice where you can run into this race condition that you access the object that was just deleted on another thread, and then you just flat out crash. So it's of course possible to handle this issue. You can account for that, but it's a little bit of work to do this right. And you don't have to worry about this in this nested setup, because this window of opportunity where you can crash the app by accessing this object just doesn't exist in this setup. The disadvantages here are that every request in one of these worker contexts on top will block your main queue. So every fetch request you execute, every save request you execute, has to go through your main context. And those are synchronous APIs. So your main context, not just your main context, your main queue is blocked for the time the background context at the top executes a fetch request. If that's a problem or not, you have to check that for your use case. Depends what you're doing. Another disadvantage is that saving a child context pushes all changes down to the parent context. So before I said when you merge save notifications, core data can discard stuff because it knows it's not of interest to the other context. Now with nested context, core data has to channel all this data down to the store. So it has to push all of this in. So if you insert 10,000 objects in the child context, core data has to instantiate 10,000 objects in the parent context, even if you don't care about them there. And related to that, every save now has to go through the main context. So every save of stuff you do in the background context has to be pushed through the UI context. And sometimes it's a very valid thing to consider if you want that. If you want to push all the stuff you're importing in the background, for example, right into the UI context, your UI might get unusable by that or something like that. So there are cases where you want to defer that and want to import in the background without having the UI update all the time, for example. And that becomes a bit less straightforward in this setup. Another disadvantage is you have no merge policies. When you work with nested context, you save a child context, all the changes are pushed down into the parent context with brute force. There is no consideration about conflict resolution. This is just a brute force push down into the previous context. It just overrides like everything. And another thing to consider, another pretty esoteric issue, is that once you work with nested contexts, you have to be aware there are weird things going on with temporary and permanent object IDs. And you can run into weird situations where you break stuff like the uniquing guarantees that core data usually has, stuff like that. But I'm not going to expand on that. It's a weird, complicated topic with all kinds of edge cases. But just to be aware of, there are some dangers there. So the question, which stack should I use? Well, by now you probably know the answer I'm going to give you. I can tell you. It's even so. What I can do, and what I try to do in a very short, compressed form just now, is I can tell you the facts. I can tell you what it does. I can tell you how it operates. But if these things I listed as advantages and disadvantages are even of interest to you, or if they don't matter for your project, I don't know. And if they matter, I don't know how to weigh them. So I cannot say this is the best setup for everything. I can just say there are all these different possibilities. And based on core data's architecture, they come with certain trade-offs. And I think it's really important to understand these trade-offs, to reason about them for your specific project, and to make a choice based on that. And to not do what we all like to do sometimes and just Google something, Stack Overflow, copy paste. This is, or I don't know, open my book, take something, copy paste. Even it's not, it's not. You will not get the best thing for your specific use case. So a related topic, which is also where I also think it's really important to understand what core data does, is save conflicts. So this is this weird thing which we all like to ignore and just ignore, or in Swift, like write the try exclamation mark save. Yeah, so just, this will probably not happen. Yeah, this is cozy. Yeah, this was a crash now, just by me saying it. So once you have multiple contexts, of course, you can run into conflicts. Like this data cannot be can be not reconcilable when you save it. Core data might say, "Hey, I cannot save that like that because things have changed in the meantime," and that's something you have to handle as soon as you do concurrent stuff with core data. And that's not core data's fault. It's just concurrency. This is hard. So what core data does is two-step optimistic locking. That means first it compares a snapshot, which is, I will say something a bit more later. It compares a snapshot, which is attached to a managed object, with the data in the persistent store's row cache when it saves something. And if those two things don't match up anymore, core data knows something has changed in the meantime. And second, it checks if the persistent store's row cache matches the data in SQLite. And if it doesn't, core data again knows somebody else has changed something in the SQLite store in the meantime, and it cannot just save the stuff, save the data. And it does that with these, if you look into an SQLite file of core data, you will see this column in the tables that is called something like zopt, Z-O-P-T. It's the optimistic locking identifier. It's just an integer which gets incremented each time you make a change. And those things are compared when you make a save between the context and the row cache, between the row cache and SQLite. And why does core data do this 2 times? Well, that's because this thing is so damn flexible that you can put this together in so many different ways. If you have the setup with one coordinator and 2 contexts, so here we have 2 contexts at the top, and both of them have this object foo. And this object foo has a snapshot connected to it, which is the version 1 in this example. The snapshot is just the state of the data when it was last loaded from the store. So now we make a change in the right context and save that. So now the snapshot in the right context and the data in the row cache has the version 2 attached to it. When you now make a change in the left context and save that, the save will fail. Oh, there's an extra save here. Shouldn't be there, this word. So this is how, when you have a setup with multiple contexts connected to one coordinator, core data has to check for conflicts on this level. But if you have a setup with multiple coordinators connected to one SQLite store, and I'm just leaving out the rest of the stack at the top for simplicity's sake, then it has to check for conflicts here too. So it does the same thing. If the row cache entry on the right coordinator changes and gets saved, well, now the row cache entry is at version 2 in the right coordinator. In SQLite, it's at 2 as well. If you now try to make a change from the left coordinator, this change will fail because the left coordinator's version identifier of this object is at 1. In the store, it's at 2. If you enable the debug output, SQL debug, you will see the queries core data does to verify that before the save. And then it will say, no, sorry, can't do anything with your save request. And then you get into this whole topic of merge policies, these nice things. You can use the system, the standard merge policies. You can define your own ones. That's a bit beyond the time we have tonight. But it's really important to understand how core data handles conflicts, because as soon as you do concurrency, you have to worry about conflicts. This can happen. You can ignore it. You can just close your eyes and hope for the best. It's edge cases, right? It just happens sometimes. But, well, you are relying on good luck then. Okay, so beyond this more technical stuff about core data, I just want to reiterate this main point I'm trying to make here. And the main point is that I really think we shouldn't go out there and look for recipes. But I think what we should do if we are trying to make choices like that, or if we try to understand why is core data not performing well, I think we should look for explanations and think these explanations through and really work through them in our mind and understand them. And once we do that, we don't need recipes anymore. We don't need anybody anymore to tell us that's the best setup. Or we don't need anybody to tell us you have to do it, I don't know, you have to configure your fetch request like that to get the best performance for your table view. Because if you understand what's going on below, you can make a much better choice for yourself because you can apply this knowledge to your specific circumstances. And every one of us is in a unique position to make the best choices for ourselves because we have this special knowledge about ourselves, about our preferences, about our prerequisites, about the specifics of our project, our constraints, our requirements. And if we combine that with an understanding, if we really have understood what's happened and reason about this for ourselves and apply it together with the knowledge about our specific circumstances, I think then you can really make a better choice than anybody like me or some guy on Stack Overflow or whoever could make for you. So that's the one point. That's the first point why I stress this and why I really say you have, in the end, there's no alternative to thinking it through yourself. And the second part why I stress this is because I think once you do that, you build these little islands of knowledge in certain areas. And I think this is a very empowering thing to do because you build these little pieces of knowledge, even if it's just niche areas, like a weird persistency framework on one platform, where you can say with confidence, now I have a good reason to have a strong opinion on my choice here in my project, because I didn't just do what Florian Kugler said in his book, but because you thought it through with an understanding of the framework and the requirements of your project. And I think this, at least in my experience, that's something that is very important to me. For me, this is just this beautiful ability we have to reason stuff out for ourselves, to not having to refer to authorities, or to not having to assign authority at all to somebody, but to be able to think this through for ourselves. And I think this is a beautiful ability we have. And in my experience, every time I use this, I think this is a very empowering feeling. And so I want to end on this very technical note and on this very non-technical note, and encourage you to do this more often, even if we all have the urge to just copy stuff from Stack Overflow from time to time, which can be also fine sometimes, right? Okay, thank you for your attention. And if you have any questions, I will be around.